Hi, thanks for joining me today. I've got another step problem I want to share with you. This one comes from 2017. It's step 3 and it's problem 4. So for those of you that don't know, step is the entrance exam you have to do if you want to study maths at the University of Cambridge. And I've already made a few sort of Cambridge step videos, so I'll make a playlist and put them all in one, and a link for the playlist will be in the description below if you want to check out some of those videos as well. Anyway, this is what the problem is. We have, for any positive function little f of x, we define the geometric mean of little f to be this function here, so capital F of y, so that's e to the power of 1 over y times the integral from 0 to y of ln of f of x dx, so the natural log of f of x dx. Normally I don't write ln, but because in this video we're going to be using ln and logs a lot, I usually write log as opposed to ln. I'm just going to be using ln here just to mean log base e, which is pretty standard. Anyway, so part 1 of this problem, we want to show that for a positive number a, where a does not equal 1, we want to show that the geometric mean, capital F, can also be written in this form here. So a to the power of 1 over y times the integral from 0 to y of now log base a of f of x dx. Part 2, we want to show that if f of x times g of x equals h of x, where f, g and h are just some positive functions, then the geometric means, so f of y times g of y, capital F of y times capital G of y equals capital H of y, where capital F is the geometric mean of f, capital G is the geometric mean of g, and capital H is the geometric mean of h. Okay, that's part 2. Part 3, where b is just some positive number. If we have f of x equals b to the power of x, then we want to show that capital F of y is the square root of b to the y, so the geometric mean of little f is just square root of b to the y. And for part 4, we kind of want to do the converse of part 3. So if we have this thing true, then this thing true. In other words, if the geometric mean of little f can be written as the square root of little f, then f of x, so little f of x, must be of the form b to the power of x, where b is just some positive number. Okay, so quite a long question, but if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so part 1 is kind of straightforward. All we need to do is use some basic log tricks. I've written down the 2 log tricks we're going to be using here, and these are very standard and things that if you're going to sit the step, you'd know anyway. Okay, so the first trick is a to the power of b is the same thing as e to the power of b times the natural log of a. And the second thing we're going to be using is that log base a of t is equal to the natural log of t divided by the natural log of a. Okay, so here a, t and b are just some nice numbers, so they're not like negative, they're not 0, and they're also maybe not 1 in some cases. So t is fine to be 1, but we can't have a being 1 because we can't do log base 1. Anyway, that's just some technicalities. We're going to be using this right here. We're going to start from this guy here, so a to the power of this expression here, and show that it's equal to capital F of y. So this thing here, well, it's already in the form a to the power of b, so let's use this thing here. This is just e to the power of b times ln a. A is just a and b is this expression here. So e to the b times ln a, let me write down the ln a first, and then multiplied by b, so that's 1 over y times the integral from 0 to y of log base a of f of x dx. But of course, if we just replace t in this thing here with f of x, we can write log base a of f of x as just the natural log of f of x divided by the natural log of a. So let's do that. Oopsie daisy. So this thing here is just the natural log of f of x divided by the natural log of a. But of course, we can bring this out because it's just a constant and it will cancel with that guy. So this is just e to the 1 over y times the integral from 0 to y of the natural log of f of x dx. And that is precisely how we defined f of y. So this thing here just equals f of y. So a pretty straightforward part 1. Let's move on to part 2. Okay, so part 2, we want to show that if little f of x times little g of x equals h of x, then capital F of y times capital G of y equals capital H of y, where they're the geometric means, and f and g are positive functions. Okay, again, this is kind of just straightforward, again, just using some log tricks. Let's start from the right-hand side, so h of y, and show that it's equal to capital F of y times capital G of y. This thing here, just using the definition, is e to the 1 over y times the integral from 0 to y of ln of h of x dx. But h of x is just the same as f of x times g of x. So f of x, g of x dx. Okay, but we can use a pretty standard log trick that log of a times b is the same as log a times log b. So you can write this thing here as just the natural log of f of x plus the natural log of g of x, like so, plus the natural log of g of x. Okay, like this. And then we can just write this as two integrals added together. So this is just e to the 1 over y times the integral from 0 to y of natural log of f of x dx times, add 1 over y times the integral from 0 to y of ln of g of x dx. All of this is in the exponent, but then we can use another exponent rule that e to the power of a plus b is just e to the power of a times e to the power of b. So this thing here, I can write as sort of the product of two e to the somethings multiplied together. So this is just e to the 1 over y, integral from 0 to y, of the ln of f of x dx times e to the 1 over y times integral from 0 to y of ln of g of x dx. And quite clearly this thing here is capital F of y, just looking at the definition, and this thing here is capital G of y. So this thing equals capital F of y and times capital G of y, like so, and we've proved what we wanted to prove. Again, kind of straightforward, some very cheap marks. You don't have to do too much apart from know your basic log tricks. Let's move on to part 3 now. Okay, so part 3 we have that f of x is b to the power of x, where b is just some positive number, and what we want to do is show that capital F of y equals the square root of b to the y. Here I've just sort of written down what we've done so far. We've shown, well, capital F of y is by definition this guy here, but we showed in part 1 that it can be written like this thing here, a to the power of 1 over y times integral from 0 to y of log base a of f of x dx, where a is a positive number which isn't 1. And the reason it's not 1 is because we can't do log base 1 of something. Okay, so we want to prove this result here, and we're actually going to be using this thing here, but you can see this is only valid for a positive and not 1, but here we're considering b positive, so we've got to consider the case b equals 1 separately. So we'll do that first. So if b equals 1, then f of x is just 1 to the power of x, so f of x is just 1. So this is the case b equals 1. Okay, f of x then is just 1, so we can just compute capital F directly from this definition here. Capital F of y then is just equal to e to the 1 over y times the integral from 0 to y of the natural log of f of x, but that's just the natural log of 1, which is 0, just 0 dx. So of course this integral is just 0, and obviously that from y to 0 is still just going to be 0, times 1 over y is 0, a bunch of zeros. This is just e to the 0, which of course is 1, but it just so happens that 1 is indeed the square root of 1 to the power of y for any y. Okay, so that's the case when b equals 1 done. It's kind of straightforward. Now let's look at the case when b does not equal 1. So this is case 2, I guess. The case b does not equal 1. And now we're going to use this thing here because we can, because b is now positive and not equal to 1. So we have that capital F of y is just equal to, and instead of using a, we're just going to be using b. So b to the power of 1 over y times the integral from 0 to y of log base b of f of x, but f of x is just b to the power of x, so log base b of b to the power of x dx. But of course we can drop this x outside in front of the logarithm, and the log base b of b just cancels, so I've got here just x. Now this is kind of straightforward. This is just going to integrate out to a half x squared. When we plug in y and plug in 0, we're just going to get a half y squared, so this is just b to the 1 over y times a half y squared. This of course just multiplies out to a half y, like so. And of course we can just write this as the square root of b to the power of y, just like that, and that's exactly what we want. Okay, so we had to split it up into two different cases, but using part 1, this part 3 was kind of straightforward as well. Now let's kind of prove the converse, which is part 4, and then we'll be done. Okay, so part 4 we have that capital F of y is equal to the square root of little f of y, and we want to show that that implies that little f of x equals b to the power of x. So here, little f of x is not only a positive function, but it's also a differentiable function, and the differentiability bit is key, because that's how we're going to solve this part. So we have f of y, just by definition, is this thing here, and in this case we're told that it's the square root of f of y, which we can also just write as f of y to the half. Okay, the first thing we're going to do is just take the natural logarithm of both sides. So this thing here just becomes 1 over y times the integral from 0 to y of ln of f of x dx. And this side here, when we take the natural logarithm, we can bring the half to the front. So it's just a half ln of f of y, like so. And we're just going to multiply both sides by y to get rid of this thing here and pop it over here. So we have this integral here equals y over 2 times the natural log of f of y. Okay, and now the differentiability bit is key here because we're going to differentiate both sides, and that kind of, well, it's certainly doable if f is differentiable, and we kind of need that to move on to the next step. It doesn't actually say differentiable in the initial in the step paper that was handed out, so that may have confused a few students, but I don't think it would have sort of confused many, because when you're actually sitting the step, this is before you've gone to uni, so you haven't really been introduced to the idea of non-differentiable functions too much, and I think it's a fair assumption to make that f is differentiable. That being said though, if I had written the step paper myself, I would have made sure it said the word differentiable in the problem. Anyway, let's differentiate both sides. So this left hand side here, just using the fundamental theorem of calculus, because I'm differentiating something which is an integral from some constant up to y. When I differentiate it with respect to y, I'm just getting the function in the middle, in the integrand, evaluated at y. So this thing is just, this side, sorry, is just ln of f of y. And on the right hand side, differentiating this thing here, we're going to use the product rule. So let's differentiate y over 2 to give us a half, and then multiplied by ln of f of y. And now let's differentiate this guy here and keep this. So plus y over 2 times the derivative of this guy here. So we're going to use the chain rule. This is just f prime of y over f of y, like so. Let's bring this half ln fy onto this side. So we actually just get a half here and get rid of this thing here. So a half ln f of y is equal to this thing here. Let's get rid of the halves now by multiplying both sides by 2. Okay, let's make this a bit cleaner. Okay, and the next thing I want to do is just essentially rearrange this to bring all the f of y's onto one side and keep the y by itself on the other side. So this will give me that y is equal to ln of f of y times f of y divided by f prime of y. Okay, so just bringing this f of y onto this side and this f prime of y onto this side, and then writing it here. Let me clean up the whiteboard and we'll continue. Okay, so we just showed that y equals f of y times ln f of y divided by f prime of y, but what I meant to write down was the reciprocal of this equation here. So obviously this thing here, 1 over y equals f prime of y divided by f of y times ln of f of y. And now you might wonder how we have to solve this, or we're just going to integrate both sides. So if you integrate the left hand side, that's just going to give us an ln of f of y. Oh, sorry, just ln of y, sorry, not ln of f of y. So integrating the left hand side with respect to y gives us this. And then we've got to integrate the right hand side with respect to y. So the integral of f prime of y divided by f of y times ln of f of y dy. And of course we're going to get some constant, so plus c. Okay, to evaluate this thing here, we're going to do a u substitution. Hopefully it's quite clear what we're going to use for our u. It's just u equals f of y. So u equals f of y. Then that of course means that du is equal to f prime of y dy. So this integral here just becomes the integral from, well, f prime of y dy is just du. And then on the bottom we've got f of y, which is u, times ln of f of y, which is just ln of u. Okay, and then plus c. But of course we have to evaluate this integral now. And again, we're going to do a further substitution. We're going to say let theta equal ln of u. So then that of course means that d theta is equal to 1 over u du. So this integral here now becomes the integral of, well, du over u is just this thing here, so d theta, then divided by ln u, which is just theta. So that thing there, and then of course plus c. And this integral here is just ln of theta. Let me write it here, ln of theta plus c. But what's theta? Theta is just ln of u. But what's u? It's just f of y. So this is just ln of f of y dy. So not ln to Generes, this is ln of f of y plus c. So we've shown that ln of y is equal to ln of f of y plus c. Let me clean up the whiteboard and we'll be at the final stage of showing the desired properties of little f of y. Okay, so we just showed that ln of y is equal to ln of f of y plus c. The next thing we're going to do is just do e to the power of both sides. So the left-hand side, e to the power of ln y is just e to the power of ln y, so the e and the ln's will cancel, and we've just got y. And on the right-hand side, we can write this as e to the power of this times e to the power of c. Now, e to the power of c is just, we don't know what c is, so we don't know what e to the power of c is, but we know it's just going to be some constant number, a constant positive number, a. So I'm going to write it as a times e to this thing here. Of course, the e and the first ln will cancel, so this is just ln of f of y. Okay, so y is of this form here. Next thing I'm going to do is divide by a, and this is perfectly fine because a is not 0. In fact, a is positive. It's just e to the power of c. And we know c is a real number, so e to the power of c is going to be positive. Dividing by a gives us that y over a equals ln of f of y, and then the next step, kind of obvious, raise both sides to the power of e. So we'll get we'll get f of y equals e to the y over a. But of course we can write this as e to the power of 1 over a, and then raise that to the y, just from exponent multiplication rules. But e to the 1 over a, again, we don't know what it is. It's just some positive constant, and we're going to call that positive constant b. Okay, so we get that f of y now is b to the power of y, and that's exactly how we wanted to write f of y, as some positive number to the power of y. And that concludes part 4. So that's the end of the step problem. In my opinion, that was kind of a straightforward step problem, the most challenging part being part 4, where we've got to differentiate both sides and know how exactly to integrate up and get to this thing here. But parts 1, 2 and 3 certainly were relatively straightforward, just using some basic log tricks and integral, basic properties like the linearity of the integral and things like that. But really, all in all, not too challenging for a step 3 problem. Anyway, I'm going to stop waffling. Thanks for watching. I will catch you in the next one. Have a great day.